Okay, so I will cover the following topics. First, I will explain why we need a software-defined hardware, and we talk about today's the FPGA development is become much easier using the high-level synthesis. And however, that the software and hardware are different. I will illustrate two examples. That is the challenge of developing the high-level synthesis. And I will talk about what benefits that you can get from the high-level synthesis, and then talk about the industry use cases. Okay, the need for software-defined hardware. Okay, so first, DARPA is an organization which is an agency for Department of Defense of U.S. So DARPA basically set the direction for U.S. college research directions. Okay, he states that in modern warfare, okay, all the decisions driven by information. So the ability to explore the data to understand and predict the world around us is an asymmetric advantage of the Department of Defense. Okay, so that thing is very crucial, and also think U.S. has the asymmetric advantage for doing that. Okay, so that's a software-defined hardware. Okay, so basically the idea is you're given a high-level program, okay, doing all kind of a compiler process, dynamic hardware and software compiler. So that's the technology they're going to develop the compiler for hardware and software such that they can run different configurations. Okay, and the end, that's the goal. Okay, here, that's the goal. That's also the goal we learned the high-level synthesis. First, compute efficiency. Okay, they said the target is within 5 x of ASIC. Today is like a 10, 1 to 2 order. That means 10 to 100 below the ASICs. They want to reach 5x. That means the ASIC is 5 times faster, not more. Okay. Another is the same programmability as current Python implementation. Okay, try to think about it. How do you do the Python programming? First, you import a lot of package and then call the functions, right? So you don't write much code. You call a lot of library and maybe do some very simple code to bridge different function code. So they want to do the software-defined hardware just as simple as doing the Python programming. Okay, not today. So we have to write RTL code, spend months in develop RTL code and doing the implementation and then debugging. Just simply like writing the Python code, and you run in the hardware. And when you run in the hardware, you can run in different configuration. Yeah. So that's the DARPA set this goal. Okay. So let's say from the high level of the observation, computational power hit a plateau. Yeah. So that's why we need an application-specific architecture. So that means that's a reconfigurable architecture. Okay. So CPU is not configurable. GPU is not reconfigurable. ASIC is not reconfigurable. Yeah. So only the FPGA. Yeah. And then we observe the rise of a custom acceleration IP market. So that means, as I just talked about, like a Python, people offer a lot of Python package. So you do need a lot of hardware accelerator IP, and it cannot develop by a company. So by providing an IP market, like before, how the big company develop the hardware IP, and then you pay a lot of money to license the IP. You pay a lot of front fee cost to license the IP. But today's the hardware IP market, just like you pay by using it. Okay, just a library put on the market, and then you code the library. When you use to do the development, it doesn't cost you any money. Okay, and then when you deploy in the system, and when it start running, then it start charging you. 为什么它 why they stop? Okay, cool. Very strange. Yeah. Let me. Oh, okay. Since there's a timer. Wait. Okay. Just like a use a cloud CPU. Okay, they charge you by how much time you use. Yeah. So they have a very low entry cost to entry to use it. Yeah. And when your business pick up and when you make money, and then you pay for the IP. So this greatly encourage people to develop all kind of IP, hardware IP. Yeah. So let's talk about the architecture. I don't compare with the ASIC because the ASIC take too much time and the cost too much. Okay. So we compare with the CPU. There's a CPU architecture. Okay, CPU because I starting my age is in the 286. Probably most of you never heard about 286. Yeah, that's a long time ago. And then the first out of all the processor comes out, and then Intel try to push their processor speed from gigahertz to 5 gigahertz per day. And so in order to run it faster, so we add more pipeline stages. Yeah. So it's a highly flexible, but it's really low computing efficiency because the processor is a traditional von Neumann architecture. So it's a low store architecture. Okay, when instruction to the other instructions, the data is communicated by register or by memory. You have to save the data to register and then load the data from the register and do next computation. So that's the kind of architecture used in today's processors. So it's a very low computing efficiency. Yeah. However, it's highly flexible, so it's general software used for general software processing. You can develop very fast. And then it comes from the GPU. The GPU is targeted for graphic video processing. So it basically is a massively parallelism in that. So that's why inside here, FPGA has a graphic and compute array. So that means they have 1,000 of processing unit. Each processing engine like a small processor. It does take an instruction. So that's called the grader code, pixel shader, or vertex shaders. Yeah. So it's a good flexibility because you use the device by using software programming, but its computing efficiency is not average. Yeah, yeah. So you use the processor for doing job with the SIMD like task. Yeah, and that's the GPU. This is a FPGA. Okay, FPGA, everything is programmable. The function computation is done in the CLB or the, I don't know why it's keep jumping back here. And the DSP, and you have a lot of memory in a sea of the gates. Yeah. So all the architecture is programmable. So that's you offer a good flexibility, and you have a good compute efficiency. Parallel computing for real-time processing, and it's low power. Okay, so it's very good for hardware solution for specific algorithm. So this gives a very brief architectural comparison. So let's compare the three. Let's look at the relative performance here. Yeah, the GPU has a 2-order performance improvement over CPU, and FPGA has a 1-order, 10 times. Okay, but compared to ASIC, FPGA like 10 to 1 or 2 order slower. Okay, and remember the DARPA goal is try to within 5x. Yeah. So it's still some way to go. Yeah. And let's talk about easier programming. Okay, the GPU, I think, although it needs specialized skill, but most of school student learn it. Yeah. So it's kind of flexible. But for FPGA, it requires a specialized skill. So not many people can develop application run in FPGA. So it's regarded as a hardware job. Okay. But HLS is going to change it. Yeah. So that's why Xilinx, the whole company spent a lot of effort in teaching the industry about HLS. Okay, so from what I can see that the area that FPGA is more compute efficient than GPU in the following area. Okay. First, GPU could not handle irregular parallelism. A lot of algorithms are not SIMD-like. For example, graph processing. Okay, a lot of the algorithmic application, they are not SIMD-like. And customized data type. And GPU 里面的 inside the processing element, that's a 32-bit floating point, and that's the hardware fix. But a lot of applications don't need that kind of resolutions. So people want to be able to customize this data type. Yeah. Furthermore, customize data path. FPGA, actually, you program your own architecture. So the architecture is programmable. Yeah. And data flow is very effective. As I said, there are 3 parallelism architecture. One is the pipeline. One is the SIMD. One is data flow. Okay. And data flow is very efficient. Okay. Data flow, those 3 data flow still can incorporate pipeline and SIMD. It's just that the data doesn't go through a memory. It goes to the next stage of a processing task. So the latency and data movement greatly reduced. So that's why FPGA shows great performance improvement over GPU. Another thing like efficient memory access semantic. For every application, they have a special way of accessing data. Okay, then the FPGA can design a special memory structure or caching structure so that it can efficiently use the data. And this is not possible with a fixed architecture. I think that these three things, they are all the FPGA's advantage. We can see how powerful is these things. So why FPGA is not as popular as GPU? Think about this question. Yeah. So it's a run efficient, it's a low power, run faster, but why today is not as FPGA is not as popular as GPU? Yeah. Okay, let's look at this. Okay, this is a research report you can reference here. So first, when you talk about B operation, okay, I'm not sure whether you can read it. This Altera FPGA, there's a Xilinx FPGA. In the middle, there's an AMD processor, there's an Intel processor, and the graphic processor. You can see the CDW computational density. That's a matrix defined for the new computing performance. You will see a lot of people talking about that. Okay, every computation takes power as a cost. So you want to have a matrix that's defined as a computational density. Computational density is a giga operation per second. The Y is power. Okay, so remember this matrix. So for B operation, we all understand that FPGA definitely has an absolute advantage because all this architecture, like Intel, that's maybe 128-bit inside data pipeline, and the graphics generally is 32 bits, 14 points. Yeah. So of course, to talk about B operation, FPGA has a much greater advantage over GPU. But let's talk about even the 14 point here. That's a 14.32. So this data type is the GPU native data type. But look at here, the FPGA still shows a higher performance, 2 or 3 times higher than the GPU. So that means that the other factors, like I said, the other factor that got into play to show the advantage. Yeah. Okay. Next, I would like to talk about the FPGA development becomes easier today. Okay, this I'm talking about software engineer. Okay, let's assume because this course like to enable software engineer to do the FPGA design. So for a software engineer, what's difficulty in developing application accelerator? First, hardware language are low level and very difficult. Okay, and then the software engineer actually know nothing about hardware design. Another thing is the software application, actually how the software interact with the FPGA. So that's a system programming issues. So I would like to address these three issues in today's FPGA development. Okay, let's talk about first the hardware. Okay, first we use a different language to develop hardware. Okay, we use a C++ or OpenCL. Look at the sample code here. How do you do the high-level synthesis? First, there are a lot of library available. This is a very simple example that video stream comes in, does a normalization, and then output to the memory. Okay, do some image processing. So when you develop an application, you will use mostly from some library. Like here, you use a VTC AI library. So these two blocks is a library. To hook up this library, you develop your own code. So this blue box is the code you develop. And then you look at the code here. Okay, that's the interface definition. That's pretty much standard things. Okay, and inside, so you develop this code, and then you code the library. Those things, yeah, you code this library. They are all libraries, and you only develop this code. So it's a very, actually, you look at here, there's not much code here. Yeah, a lot of it just code the library. Yeah. So you take this code, the high-level sensor will automatically compile, and then generate the bit string, and then you load into the FPGA. Okay. Further, this whole development speed up by library. We talk about those library offered by Xilinx. And also you have a lot of partner libraries. Yeah. So it's pretty much close to the Python programming, as long as you have all the necessary library available. You can develop application very quick. So let's talk about, okay, so software engineer, actually we know nothing about hardware design. Yeah. But remember, since Intel introduced is a multi-threading processor, like a hyper-threading, and later introduced multi-core processors. Intel has spent like a decade or 2 decades of education to the industry to do multi-threading programming or parallel programming. Okay, so most of the software engineer has the concept of parallel programming, and the parallel programming does help in the hardware design. So, so we have to say most of the software engineer, they can think parallelly, especially in the area data level parallelism and text level parallelism. Data level parallelism, basically you partition your data sets and then have a separate hardware computing unit address process each data. And within each processing flow, you use a text level parallelism. You do the processing in pipeline. Yeah. So this is today's software engineer to develop efficient application. So this is actually very much like a hardware design. For example, like this data parallelism, SIMD is a typical data level parallelism. And text level parallelism is like a pipeline or data flow. Okay, and when you run multiple thread application, you definitely involved in doing the thread synchronization. Okay, it's a similar like in the hardware. Okay, the hardware, there's a protocol or synchronization between the two hardware modules. Yeah. So for software engineer, you actually think parallel already. And when talking about low-level instruction level parallelism, actually it's done by the processor or compiler. So this part you don't need to worry. Yeah, from the software programmer point of view. Okay, the next one is okay. So I put part of the code into the FPGA. So how does my software communicate with the FPGA? So they involve a lot of system driver, system programming. Yeah. So fortunately, all those FPGA vendors, they provide the whole platform. Okay. So you don't need to worry about it. But there are certain issues you have to take care of. Okay, let's take a illustrate an example. Let's say this part is your application program. And then you do some profiling and decide certain portion of the application, like you want to put into FPGA. So there's a accelerated functions. So right now you move this accelerated function into the FPGA. Okay, so then what happened? Before those two part of a code, you communicate by the processor register or using the cache memory. And actually, these two parts running in the same address space, same virtual address space. So it's transparent. You simply call the function. Yeah, and the function argument either save in the register or in a stack maybe in the cache. Okay, you don't need to handle data movement. Okay, and the synchronization is very straightforward. When the function finish, it just return. Yeah. So once you move here, a lot of things happens. Okay, it involves data. You need to physically move the data from the memory to the FPGA. You need to do the synchronization. So who handle it with that? Okay, so to do the communication and data movement from the FPGA side, you need to have a DMA engine, and there's a hardware component that have to build in besides the accelerated kernel function. So these are provided by the FPGA vendors. And corresponding to this hardware component IP, Xilinx or FPGA vendor provide the drivers and the API. Okay, so you communicate with this accelerated function through calling the API. And the API communicate with the OS drivers, and then it communicate with the infrastructure component here, and then move the data to the memory so that the acceleration function can access. Well, all those things is done by the infrastructure component. You just need to know what is the API here and what is the interface here. Okay, when you partition over, you know the host program, how to access this, you call certain API. You have to learn that. So in the lab 3, it's used OpenShield. Okay, and the kernel function here, so we will define the I/O interface, the HLS I/O interface in later class. Yeah. So by doing these two, so you need to understand the mechanism so that you can seamlessly integrate the accelerated function with the host function. Yeah. So this is what we need to learn in this class, besides how to do the kernel optimization. And especially, you need to pay a lot of attention to system optimization. How do you schedule the data movement efficiently, such that all the data move across the tool, the overhead can be minimized or disappear. Remember, when you run in the same processor, there is no overhead. Right now, the data has moved through the I/O bus, go the long way to the other side. Yeah, that's the price you have to pay off. Yeah. So you have to know the whole system mechanism, and then to decide whether you want to do application acceleration. There are certain application characteristics that may not suitable for application acceleration, simply because all those overhead involved. Okay, so this we also need to learn this in the class. Okay, it's time to take a break. I have a few questions. Yeah. First, give one reason why FPGA is not as popular as a GPU. What happened? Okay. Oh, here. Okay. There's a question session. Give one reason why FPGA is not as popular as a GPU. Okay, you can write your answer in the chat. The second question, why is the CDW? Okay, the third, when some functions are moved to FPGA, what statement is true below? So there's multiple choice. So they involve actual text synchronization overhead. There is actual data movement, or host software and FPGA function cannot run in parallel, or overall system power is reduced. Yes. Okay. Let's look at the chat. Oh. Everyone can answer the question. Okay, this one answer because GPU is more flexible than FPGA. Okay, and more flexible in terms of programming, right? Or the architecture is more flexible. Yeah. Actually, FPGA is totally programmable architecture. Yeah, the GPU is still hardwire, limited by the existing architecture. So I would say that the GPU is more easier to programming than FPGA. Okay, someone answer FPGA require more specialized skill, right? Yeah. Basically, yeah, you do need to have a hardware concept. Yeah. Anyone can answer the third question? That's kind of easier. Oh, A, B, D. Okay. Oh, someone. A, B, D. A, B, D. What statement is true? A and B is right. Okay. D is hard to say. Okay. When you remember that when you move a certain function to FPGA, you have to move data to the FPGA. And the data is moved across the I/O bus. And the I/O is very, very power consuming. Yeah. So the gain you got from the computation part maybe will offset by the data movement across I/O. So the overall system power reduced. It's really hard to say. Yeah. So you have to be very careful design it. And C C is not right. Yeah. Host software and PGA cannot run in parallel. Okay. When you move to the FPGA, so the host and FPGA can run concurrently. Yeah. Okay. Okay. Some answer the question. So let's stop the question session here. Let's move forward. OK. Although a lot of industry effort try to make the FPGA design easier by using high-level synthesis. However, the software and hardware actually are quite different. Yeah. Let's see. I will illustrate two examples. One is the data dependency. Okay. The data dependency really affects your pipeline parallelism. Okay, there are three kinds of data dependency. One is read after write. Look at this simple code. If you want to pipeline it, okay, you have to read A0 and multiply and save to A1. And the next pipeline comes in, assume the the pipeline is one cycle. Then you have to do the same thing. Okay, in here, we observe that you store A1 later than you read A1. So that's the read after write dependency. And that's a true dependency. So you cannot pipeline with the II equal 1. You have to move over here. Delay two more cycles. You have to save A1 and then load A1. Okay. Another kind of data dependency is write after read. In this code, I probably don't go much into the details. Okay, that because in later session we will discuss this. And in here you can see that input A1 and store A1. So that's the write after read. Okay. So you cannot. So it's very likely the read may read the new value instead of original value. Another is write after write. In this example, you will see the pipeline. There's a store B3. There's a store B3. In two iteration later, you actually store B3 earlier than the previous store. There's a write after write. Okay. So when you write the program, either the compiler or processor handle all this dependency, resolve this for you, and try to pipeline efficiently. But when you design using the HLS to write this code, you don't have an underlying hardware. So there's no processor, no compiler does all the work for you. So you have to study the code and apply techniques to avoid the limitations. For example, in processor compiler design, the write after read or write after write, they are not true dependency. They can be resolved by doing the renaming, register renaming techniques. Okay. Then, so when you write your HLS code, you have to apply register renaming techniques in your code in order to do the pipeline efficiently. Otherwise, the synthesis HLS compiler will delay the next line pipeline cycle. They have to delay until all the conflict resolved. Okay, although that you can write this code is simple, but when you synthesis, the performance is definitely not as you expect. Okay, that's one thing. Okay, let me take another example. The software C++ and hardware, they actually behave differently. Remember, we use a high-level language, C++, to do the design, and we do the software simulation, and we want the hardware result exactly the same as the software. Otherwise, there's no point using the high-level synthesis. If a software simulation result on hardware is different, then this thing cannot work. Yeah. Yeah, but hardware has a specific behaviors. For example, let's take this example. There's a very simple and typical mini machine. Okay, machine. Okay, so you write this code like this way. Okay, you have a register here. You declare this variable L. L is a static. That means allocate a register. L represents the flip flop, and you write the code. There are two operations here. The first one is input I1 times the register L. I should spell. Yeah. Okay. And then the register L is I2 times the L value plus. Okay. First, you have to write the code in exactly the order because you have to take an O value over L. The output is the O value of L before you assign L. If you switch the order of these two, the C code will behave different from this hardware. Okay. And then second, let's put this mini machine together. Okay, that's quite simple. You just fit the output of the first module to the second module. Okay, so first you have a temporary variable here. So you call the first function foo. Take a I, okay, and produce an output temp. And temp pass to foo, get the output O. Okay, it can work. This thing can work, no problem. Let's take another more complicated example like this one. This one a little bit complicated because there's a feedback loop. Okay, if you write the code, the same code, okay, so this output is says temp 1. This output is temp 2. Okay, let's look at the code. So you create two intermediate variable. So the first one, you fit I with temp 2. Okay, that's temp 2. You get result temp 1. Okay, and then you take the temp 1 to generate the temp 2, and temp 2 assigned to output. It looks simple, right? Just based on the coding, based on how you connect them, then you write your code. Yeah, but this thing won't work. Why it's not work? Because the temp 2 change, right? It cannot refer to this one. You know, the temp 2. So when you evaluate here using the O value of the temp 2 actually change. When I change, the temp 2 change too, right? Look at this path. Okay, when I change, temp 2 change, but temp 2 not able to evaluate yet, right? So you use O temp 2. Do you understand? When you propagate, when you change I, at the same time, temp 2 change. But temp 2 has to be evaluated by the second module, but the second module haven't been called yet. So when you simulate this hardware and the C code, run the C code, the result is different. So that's a big trouble. Remember, when we develop high-level sensors, we want C code and hardware behave exactly the same. If they are different, this thing cannot use. We cannot use these kind of things. What you simulate in C is different from hardware behavior, right? Yeah. So, but this is not without solution. You can still solve the problem in the course structural design I will introduce. But you just need to strictly follow certain programming guideline to do that. Yeah. So in summary, a software statement evaluate once in a sequential manner. But in hardware, especially hardware doing a simulation, that's an event-driven hardware schedule. Can be out of order and re-evaluate. If the assignment, the right-hand side variable signal change, that statement will be re-evaluated. That's a hardware behavior. But for software, it's sequential going down. You will not go back to re-evaluate that. Yeah. So in software, C program statement are evaluated in a blocking manner. But in actual hardware, it's non-blocking. It run concurrently. Yeah, in here, so I want to point out that high-level sensors do have some tricky things that you need to learn. Yeah. Okay, high-level sensor benefits. Okay, let's see. First, the high-level sensors is really benefit the design for patient productivities. For high-level sensors, using the high-level sensors for a designer, you only take care the functionality, architecture, and constraint. Okay, and you leave all the other things like you write the equation, the schedule of operation, the finite state machine coding, error reduction, timing of pipeline register, where to add the pipeline register, or how the data path component can be shown. All these are very time consuming and error prone. So since it's error prone, so you spend a lot of effort in doing verification for using the RT design methodology. So people does all kind of design style and try to evaluate its productivity to give it this report. So for the first design, you can be 10 to 15 times faster. That means the the time to market time is greatly reduced. And it's even promising if it's a derivative design, it's 40 times faster. But in terms of a quality of a result, sometimes it will be less than RTL code, and sometimes even higher than RTL code. We will see why using high-level sensor sometimes the result is better than manual RTL design. Okay. Another benefit using HLS is broader IP reuse with C++. Okay, we use a Verilog code. We know people use a Verilog using their parameterized way to coding the RTL code in order to make a IP. Okay, but parameterized Verilog code is very limited. Okay, not as powerful as C++, because C++ is intrinsically an object-oriented language, especially it has a template and class. Yeah, we will be addressing how to use a C++ template class to design the IP. That's a very important design methodology. When you use C++ to design the functionality of microarchitecture coded in IP, but implementation detail is not coded in the C code. Okay, what's the implementation detail? Like the finite state machine, you don't code the finite state machine in C++. So the system still do it for you. You don't instantiate data path components. You don't actually instantiate multiplexer. You don't put the pipeline register. All those things are handled or produced by high-level synthesis compiler. Yeah, based on your design target. So with the same behavior IP can be very easily targeted to different design criteria. For example, I want to design to target high performance or low power or even low smaller area. You can just use a very high level pragma or directives, specify that, then let the synthesis to do all the work for you. Okay, so that's why you can design very effective IP, because when you design an IP, people take the IP may use it in different application cases. Some want a very high performance IP, some want to have a very low power IP. So you can have a single code to address all different requirements. So this is a very, very important benefit. Next, let's talk about improve quality of a result. Okay, why using the HLS you can get actually better than manual developed RTL code. One thing is you have a advanced optimization algorithm. Remember, you write the same piece of code and the compiler techniques continue evolving, continue improving. That means your resultant RTL code getting better and better without spending your effort. People still continue provide much efficient compiler. Yeah, and then your design will getting better and better, and without you spending any of your effort. For example, like in next semester, I teach the prefix sum. That example. Okay, and that example have to use rigid renaming techniques. So I code. So you have to restructure the code so that they can run the pipeline efficiently. And that time we're using the 2019.2 version of the tool. You have to manually doing those code change. Using the 2020.2, that's the version of tool you are using now. And we find out the compiler can take care of that. they already put in the region renaming techniques in their compiler, yeah, to improve its pipeline. Yeah, so that's a very big advantage. You leverage on continual improvement on the compiler. Another is it allows more design space exploration. So you can very quickly create many different implementation from one single description of the design. Okay. So let's say that SMID parallelism. You can write the code using the C++ syntax. For example, you can write internal the hardware. Okay, you go back to you have a data type, suppose int with n. There's an n-way SMID. Okay, and just write the code, and then you can always change the n to provide different parallelism of the SMID design. So for example, I use a very small FPGA. I could not afford that many parallelism in SMID. So I simply change code n small number. Then I can generate design, feed into the small FPGA design. Yeah. So it's a very powerful. Yeah. And in here I list the table here simply to illustrate the QOR. Okay. And this is from a paper. This paper they try to compare. That's an image processing algorithm. So they hand optimize the design using RTL, or compare with using the HLS. So the RTL code actually is hand optimized specific architecture for different algorithms. Let's look at the result. For this case, stubble filter, the high level sensor is a little bit worse. Okay. So if you look at the Gaussian filter, you have a better efficiency, better lower resource use, and you get a higher performance. Yeah. For more for logic, it's worse than the RTL. Histogram is about comparable, or this one flip-flop is better. Yeah. So you will see HLS and RTL, hand-code RTL, the result kind of comparable. Yeah. Okay, so HLS in today's technology could achieve a pretty good quality result. And from all various reports, I see consistent result. Okay, let's introduce the industry use case. Yeah. Okay, the strong advocate for the high-level sensor is NVIDIA. Okay, there's a white paper published by Mental. That's an evaluation with the NVIDIA, and that's the data NVIDIA provide. It says that it's 10 times the improvement in RTL design, and the performance is within 2.6% from the RTL in cycle count. So performance-wise, it's a little bit less than RTL, but it's pretty much comparable. And less design effort. Okay, and we see the C+ function verification, the runtime is 500% less resource than RTL. Okay, and what's promising is they can make a rapid product change possible. For example, they change the happens from 8-bit to 10-bit only in 2 weeks, and change different foundry process from 20 nanometer to 28 nanometer only in 3 days. So for those company that the time to market is very important. Yeah. So that's the report NVIDIA provides. Let's look at another strong advocate is Google. You know, Google will never be a hardware IC design company. they put their accelerator in the data center. So they use so in Google, they are all mostly are software engineer. Okay, so they prefer a software approach to design the hardware, and that's the result they publish. So time to verify RTL, that means the design process is 2 times faster. Yeah, and you look at the design complexity. If you use a C++, only 69K lines of code, and if you use a Verilog, it's 1.2 million lines of code. So purely from the code size, you will know the complexity is greatly reduced. And Google also report the simulation speed is 500 times faster. And those two companies report the same numbers. And he says it's a software-like process and allow less stage algorithm change. Yeah. And if you look at that their block diagram, all the red block are developed in HLS. And all those blue area is for I/O interface or for the structural component like a FIFO or memory. Yeah. So pretty much the whole chip can develop with RTL, with the C++ high-level synthesis. And another advantage is for each module design, since they are written in C, okay, first they have the whole system partition, and each has a C code. Okay, so people can optimize, turn into an HLS, and verify that with the other part of C code. So each module can develop in parallel and verify in parallel before integrate. And this is not able to do in Verilog RTL design. Yeah. So that's why they speed up the development process a lot. Okay, that's another example is using the beamforming techniques. That's the RTM. Basically they implement the RTM algorithm. Okay, so it's developed by a software engineer. Okay, basically take the RTM algorithm and take 1 month to describe in RTL or in the C++. So they developed that in 1 month. So it's completely described in C++ and only less than 500 lines of code. Yeah. And key is there's a software engineer doing this FPGA design. Okay, this is another example. That's a message intelligent applied. That's a semantic supercomputing for natural language processing, natural language understanding. So we use a semantic folding algorithm, and that is very computation intensive. If you watch the white paper or look at the YouTube, the founder to explain that their company, because they don't invent this algorithm. They say my company, the core competence or my company's contribution is how to do the efficient computing with this algorithm. Yeah. So that's let me think about Taiwan industry. I feel like in Taiwan industry, most are doing the manufacture, and the product they produce has very little value added. For example, the company, Taiwan company, they design and manufacture in FPGA board. And they told me that they have a pretty good profit margin. They sell this FPGA card, they can have a 70% profit margin. It's really good. That's true. But when they sell to the SI company, they put in the software and then sell that hardware, the whole system. That's 5 times 500% of a profit margin. Yeah. So I'm thinking that in Taiwan, because the whole hardware actually is developed by a software approach. So if you want to come out to start a company to provide service, and today's all the service requires smart service. Like this company, they provide the natural language understanding. Okay, they can automatically classify message based on semantic meaning of the content. Okay, that's a pure software service. But in order to do that smartly, that you need another computation. So if you know the application and you know how to turn the application into accelerated application, you have a very unique advantage, and you can provide a lot of value for the product. Yeah. So I think Taiwan should have more people know high-level synthesis, and combine with the application and turn into the application appliance. So that's my last slide. Great. So at the final remark that I like you to think more about application acceleration appliance. So when you study, then watch out uh, the applications and see in any area that you can speed up or do the application acceleration. Yeah. Okay, that's the question. The first, in both NVIDIA and Google use cases, what benefits the most from HLS? Okay. Another example, why can HLS provide better Q&R, quality of result? Either advanced optimization algorithm, or designer has a greater control on implementation details, or simply because the HLS designer are smarter. You guys smarter, so that you can get good quality result or allow more design space exploration. Yeah. So you can answer. The first C and D, right? Yeah. The second question. Nobody choose C. The second question. Oh. A and D, advanced optimization and allow more design space. Yeah. Okay. In here, I want to specially address. I know double E student, you are good at the hardware design. So actually, that's your burden. You know hardware, sometimes it's a burden for you. So I remember I watched the student write the code. They write the code like an RTL. Every detail, so much detail. So that if you write such detail, then you leave no room for the compiler to do optimization for you. And your code won't be adaptable. Yeah. So try not to do fine control on implementation detail. You want to think architecturally, but don't think implementation. Try to avoid implementation. If you guys go at the RTL code, you get used to write the detail control. Yeah, you try to avoid writing C code like that way. Yeah. Okay, so 结束。